So we know that if we have a charged particle and we put another charged particle in its vicinity, so say a positively charged particle here in the vicinity of this positively charged particle, this particle will feel a force F that drives it away from the other particle. Also this particle will feel a force, but for now we concentrate on this particle. So we may wonder, so what is it that transmits the force onto this particle? They're not a physical contact. It's not like if I would be pushing this board, it would fall down because of the force I exert on it. These particles are separated, but still this particle feels a force. Well, the origin for the force is what we call the field, and in this case, an electric field. Now that may sound a bit abstract, but actually we are very familiar with a field transmitting a force. So if I hold this marker here, it will feel the gravitational field of the Earth. So a force is exerted on the marker, and if I let it go, it will fall down. So it's the same for the electric field as it is for the gravitational field. Now, the magnitude of the electric field we indicate with the letter E. And the electric field E is given by the force on a particle divided by the charge of that particle Q. So in this case, it's the charge of this particle Q. So that means if what we know from Coulomb's law, that for a point charge, I draw this point charge here again. So if this point charge has a magnitude, which I now indicate by Q star, then the electric field around that particle in magnitude is given by K times this Q star, so the magnitude of this charge here, divided by R squared. So this directly follows from the Coulomb force on this charge here, which is given by K Q star times this charge Q divided by R squared. And of course, the electric field has a vector character, which is given by the vector direction of the force. So how will this electric field look like? Well, for this positively charged particle, it will always point away from the particle. So we can indicate that force everywhere around the particle, but in practice, we also indicate the electric field with what we call field lines. So the field lines in this case, I'm drawing the field lines here. So they point outwards from the particle in this direction. We've seen that the force on another particle also falls with R squared. It's the same for the field. So we also see from this image that if the field lines are closer together, the forces are stronger, the field is stronger. If they are further separated, further apart, the electric field is smaller. Now there's one important situation that I want to bring to your attention, and that is the electric field generated by a charged plate. Or in this case, I will draw it as two charged plates. So one positively charged, one negatively charged. And so the field between these two plates will point in the direction from the positive charge to the negative charge. So this is the direction of the field, which means that the field lines here will run between the plates. So here, here, here. Now we can already see from this simple picture that the spacing between the lines is the same everywhere if we move further away from this plate and closer to this plate. And that is the important situation in this case. So the magnitude of the electric field for this situation is constant. So it does not fall smaller with distance from the plate or the position between the plates. And so if we have a particle in between the plates here, so if I have a negatively charged particle here, it will feel a force pointing it towards the positive plate. So a force F here. And if I would move this particle around, if I would position it here, the magnitude of the force would be the same. If I have a positively charged particle, it will feel a force in the opposite direction towards the negative plate. And if the magnitude of these charges would be the same, the magnitude of these forces would also be the same.